Hello students, Professor Nugent here. In this video we're going to begin Chapter 11. We will discuss regression with a binary dependent variable. That is, we'll look at a variable that on the left hand side has only two outcomes. There will be three models that we look at in this chapter. We'll look at the linear probability model, and then we'll look at probit and low-bit regression. We'll discuss estimation and inference in probit and low-bit regression. And we'll conclude the chapter with an application to racial discrimination in mortgage lending. What is different with binary dependent variables? So far, the dependent variable y has been continuous. Examples of continuous dependent variables include district-wide average test scores, where the district-wide average test score could be anywhere between, we need a drawing, let's draw here. This could be anywhere between something like 300 and 800. Or a traffic fatality rate could be anywhere between 0% and 1%, 100%, perceivably. So what if y is binary? For example, getting into college or not getting into college. We could think about the explanatory variables of getting into college as being high school grades, right? SAT scores, and other demographic variables. These things could explain whether you get into college or do not get into college. Another example would be smoking or not smoking. So what could explain whether a person smokes? It could be such variables as a cigarette tax rate, income, and other demographic variables. What about whether an individual's mortgage application is accepted? So accepted or denied. Again, you have a binary outcome. And such things as race, income, house characteristics, marital status, all these things will be important for predicting whether a mortgage application is accepted or denied. In this chapter, we're going to focus on the mortgage denial and race example for studying the binary dependent variable scenario. In this example, individual applications for single-family mortgages made in 1990 in the greater Boston area make up our dataset. There are 2,380 observations collected under the Home Mortgage Disclosure Act. The dependent variable is whether the mortgage is denied or accepted. Independent variables include income, wealth, employment status, other loan and property characteristics, and the race of the applicant. We're going to use these independent variables to predict whether a mortgage is denied or accepted, and we'll look at the race of the applicant to help us think about whether there is racial discrimination in mortgage acceptance or mortgage denial. So the linear probability model is a natural starting point in thinking about binary dependent variables. And we'll look at the linear probability model with a single regressor, where yi is going to be our binary dependent variable. All right, yi will only take on one of two values. And for beta 1 is going to be the explanatory coefficient. And we have to think about what this means when y is binary. We also have to think about what the line beta naught plus beta 1 times x means when y is binary. For example, we'll look at what does the predicted value of y hat mean when y is binary. These are important questions that are a little bit different when we're working with the linear probability model and when y is binary. So let's try to answer these questions. How to interpret the coefficient? What does the line mean? And what does the predicted value mean when we have a binary dependent variable? In the linear probability model, the predicted value of y is interpreted as the predicted value that y equals 1. Alright? That's the predicted probability that y equals 1. Beta 1 is the change in that predicted probability for a unit change in x. Okay, that's the change in the predicted probability for a unit change in x. So if y equals 1 represents mortgage denial, then the predicted value of y is the predicted probability that a mortgage is denied. And beta 1 will represent the increase in the probability that a mortgage is denied for an increase in, say, number of bad loans you have on your credit or something like that, whatever is represented by x. Now here is the math. Our linear probability model is given by this equation with the big nice rainbow star. yi is equal to beta naught plus beta 1 times xi plus ui. When y is binary, the expected value of y given x is equal to 1 times the probability that y equals 1 given x plus 0 times the probability that y equals 0 given x, which is equal to the probability that y equals 1 given x. Under the least squares assumption, number 1, the expected value of u given x is 0, which tells us that this line, expected value of y given x, for all observations I equals 1 through n, can be described by this expectation, which simplifies to beta naught plus beta 1 times xi. So the probability that y equals 1 given x is equal to beta naught plus beta 1 times xi. So we call this the linear probability model because our predicted value is a probability, and it is linear in the right-hand side variables. Okay, this is that predicted value is a probability. All right, so the expected value of y, given that x is equal to some value x, that's equal to the probability that y equals 1, given that x is equal to x. It's a probability that y equals 1 given x. Yes. So y hat, that's the predicted probability that y equals 1 given x. Again, we think about this as being like the predicted probability that mortgage is denied, or the predicted probability that you get into school, the predicted probability that you are a smoker. This is what we're thinking about, and that's what y hat represents. It's a probability. It's a predicted probability. Beta 1 is going to be the difference in that probability that y equals 1 associated with a unit increase in x. So beta 1 is the probability that y equals 1, given x is equal to x plus that change in x minus the original value, the probability at the original value of x, all over the change in x. Again, we're thinking about like the increase in probability that you are denied for the increase in bad loans in your credit history. Let's look at what the regression line looks like. So in this chart, we have probability deny on the left-hand side, where 1 equals mortgage denied. Here, you see that here. And 0 equals mortgage approved. You have all of the observations plotted for different payment to income ratios. And you can see for payment to income ratios that are pretty low, say below 0.3, a lot of these are mostly mortgage approved. There are a couple which are denied at 0.3 and below, but most 0.3 and below are mortgage approved, which is what you would expect for a low payment to income ratio. The less amount of your income that has to be attributed to your mortgage payment, the more likely you are to be approved, all else equal. And what we see up here, the higher fraction of your income that you have to attribute to your payment to the mortgage, the more likely you are to be denied. And then what the linear probability model does is it takes a linear relationship between the probability approve and probability deny. And the tricky thing about this is that you can see that for low payment to income ratios, we may be predicting negative probabilities, and for high payment to income ratios, we may be predicting probabilities above 1, which are infeasible. So this linear probability model has some caveats. It has some problems. The linear probability model works pretty well for data that is not very small or very large, where the probabilities are not very close to 0 or very close to 1. But when we get close to 0, close to 1, then the linear probability model starts to fail. Let's continue looking at this example. We are predicting a probability that an applicant is denied, and the linear probability model is probability denied equal to negative 0.08 plus 0.604 times the payment to income ratio. Now let's ask, what is the predicted value for a payment to income ratio of 0.3? This is the probability, the predicted probability that an applicant is denied, given that the payment to income ratio is 0.3. We'll plug in 0.3 into our linear probability model up here, and we get negative 0.08 plus 0.604 times 0.3, and that's 0.151. So the probability that an applicant is denied, given a payment to income ratio, is 0.151. You have a 0.151 probability of being denied, given a payment to income ratio of 0.3. We can calculate effects, so we can think about the increase in the payment to income ratio of 0.3 to 0.4. To do that, let's look at the probability of deny given the PI ratio of 0.4. Should see 0.4 here. Plug in 0.4 and we find the probability of deny given the payment to income ratio of 0.4 is 0.212. We can take the difference and the effect on the probability of denial of an increase in the PI ratio from 0.3 to 0.4 is to increase the probability, the predicted probability, by 0.061 or by 64 percentage points. Alright, so we increase the probability of denial by 6.1 percentage points if the payment to income ratio increases from 0.3 to 0.4. What if we include black as a regressor? Then our regression is predicted value of deny equal to negative 0.091 plus 0.559 times the payment to income ratio plus 0.177 times black. The predicted probability of denial for a black applicant with a payment to income ratio of 0.3, let's plug in 0.3 into the linear probability model and black equals 1 into the linear probability model, and the probability of deny is 0.254. We can do the same for a white applicant, so we plug in 0.3 for the payment to income ratio and black equals 0 for the dummy variable, the third term in the regression, and we find probability deny is 0.077. The difference between probability deny for a black applicant with a payment to income ratio of 0.3 and the probability of deny for a white applicant with a payment to income ratio of 0.3 is 17.7 percentage points. And the coefficient on black is significant at the 5% level. So what this is telling us is that there may be racial discrimination in the assessment of mortgage applications because black applicants are being denied at a higher rate than white applicants at the same payment to income ratio. There's still plenty of room for omitted variable bias, so we want to control for other things like demographics. What we want to be able to do is say the probability for denial for black applicant, or rather what we want to do is compare two applicants who are exactly the same except for the race. And if their probability of denial is different, then we can say that there is racial discrimination in mortgage application evaluation. So we need to bring in those demographic variables so that we have the ability to compare two applicants who are exactly the same except for their race and then evaluate that dummy variable. In summary, our linear probability model will model the probability that the outcome variable equals 1 given your independent variables as a linear function of your independent variables. The advantages is that this model is simple to estimate and interpret. The inference is the same as for multiple regression. We will need to use heteroscedasticity robust standard errors. And because it's linear, then the changes in probability over the domain of x are constant. The disadvantages, the linear probability model says that the change in the predicted probability for a given change in x is the same for all values of x, but that doesn't make sense. So it makes it easy to interpret, but it doesn't make sense. As we saw, as you get very close to 1, that can actually imply predicting probabilities greater than 1 or predicting negative probabilities, but instead what we think we would see is some nonlinearity in the prediction and the probabilities as you get close to 1 or close to 0. So these disadvantages can be solved by using a nonlinear probability model such as probit and logit regression, and we will discuss these models in the next video.